anyway, right? So today we will move to another chapter, right? So I'm glad that you survived the interrupt chapters. That's a very important chapter, and expect to have several questions from that chapter in the final exam. So now we move to, this one is kind of very, similar to chapter 2, right? Chapter 2, you learn about integer representation. So now today we will learn about fixed point and floating point arithmetic, right? So in chapter 2, we talk about integer only, kind of, right? So we don't talk anything about that. But please remember that life is not just integer, right? So you have to deal with real number, okay? So 2.1, 32.25, something like that. So, and you have to somehow, have to instruct the computer to do that as well. So that's why the computer, the hardware, need a way. We need a way to represent a real number using a binary pattern. Can you wait a little bit? Let me stop the phone over here. It's too early. Okay, very good. So for real number, the two popular representations are fixed point number and floating point number. Of course, there are pros and cons to use one of them, right? So I can tell, let me go to the second slide. I can tell you about the pro and con, okay? So for fixed point representation, remember all fixed point or floating point, that's for real numbers, okay? From today, we will talk about binary real numbers in this lecture. So for fixed point, you can have unsigned or signed, and then for the floating point, we will learn about follow the IEEE standard 754. So you will know that very soon. If not today, then it will be next week. You will know them all. So what are pros and cons of using this thing? Okay. So fixed point presentation. The calculation is very simple. It's like integer. Okay. But for floating point, it's actually slower and more power consumption. So that's why when we did the research, for my research, for example, for machine learning research at Stanford, we did a lot of calculation. Machine learning, right? Tons of calculation. And if you don't pick the right presentation, the power consumption will be a lot more. So that's why we really have to trade between the accuracy, right, and the cost, the energy cost, and the performance cost as well. So we try to use fixed point over here to reduce the energy consumption, and it is very fast too. It's good that it's very fast, right? But however, the resolution is not that good, okay, for the fixed point over here, and it has the limited range. For example, maybe just for example, from 0 to 2000 or whatever, right? So a smaller range. But if you use a floating point, you can represent a much bigger range, okay? But of course, the downside is it's lower and more energy consumption, okay? So what are they? So the next question is, what are they, and how do you use them for your calculation, okay? So let's start with the simple real number representation first, right? And that's the fixed point representation over here. Okay, so, and for the fixed point representation, you have unsigned and you have signed representation. So let's talk about the unsigned first. So whenever you see something like Uqm.n, that is the unsigned fixed point number. Okay, so for example, so let's learn about it. For example, if you have a binary sequence, binary numbers of n plus n bits. For example, we have, let me see over here. Yeah, for example, if you have a binary number of a bits, okay, a bits like this, right? And you want to use that a bits to represent a real number, right? So one way to do is this. One way to do is you can set aside n bits out of 8 to represent the fraction, and then the remaining n bits to represent the integer, the portion in front of the decimal point, right? In this case, the binary point, right? So, for example, this one, if you have, just forget about the dot over here, right? So 0, 1, 1, 0, 1, 1, 0, 1, right? If you don't have the dot, okay, if you don't have the dot over here, and if it is unsigned a number, so what integer is that? Can you tell me? What integer does this binary, 8-bit binary number represent? Can you, anybody have the calculator there? So, so this is going to be 1, 2, 4, 16, 32, 64, 128 something, right? So let me bring up very quickly. Let me bring up the calculator over here, right? So let me see binary over here. Let me type it in 1101 101. Okay, that will be 109. Okay.
Is that supposed to be the value of 13.9?
Right. But today we like to use that thing, the same binary number, right, to represent the real number. Okay. And of course, the computer doesn't know anything. The hardware doesn't know, right? But you are the programmer. You will kind of implicitly say to your friend, okay, I will use a fixed number, a bit over here for the fraction, maybe 3, for example. In this case, if I use 3 only, right? And that's what the name fixed point. 6 point is because the radix point here is fixed at one location over here. So if you have that implicit agreement that the last 3 bit will be for fraction, so the same binary pattern, right? What is the real number? Does it represent? Do you know? If you want to know, you follow this formula for me, okay? So the real value of that fixed point number is equal to the number that represented by the n bits over here, okay? And the number here, the number here represented by n bits and multiply to or divided by 2 to the power of n, right? So for example, over here, if you look at over here, and I ask you, if we use 3 bits to represent the fraction, what value is that? So you just look at over here and you look at over here, right? The power for the first 5 bits over here, it represents 13, right? So that's why the number will be 13. How about the fraction? The fraction here is 101 is 5, right? And you multiply with because we use 3 bit over here, n equal to 3. So 5 multiplied by 2 to the power of minus 3, basically divided by 8, right? So that will be 0.625, and you add the 2 together. So you will see that the real number it represents is 13.625. Wonderful. Okay, so you know how to calculate the real number that a binary sequence represent. Okay, for fixed point over here in this case. Okay, so now let me trick you a little bit. Okay, so now use the same pattern over here. Use the same pattern 0, 1, 1, 0, 1, 1, 0, 1. Use exactly the same number. But I will tell you now I like to use 4 bits for fraction and 4 bits for integer. Basically, I will tell you what will be the real value of this binary number. Assume that I follow the format fixed point, unsigned fixed point, and n equals 4, and n also equals 4. So what will be the real value of that binary number? Can you tell me? Please respond. Okay, so let's see. I'm looking at. Wow, it seems to me that many of you answered the last question correctly. Wonderful, thank you. So now I just modify a little bit. Okay, so the same binary numbers, but I will tell you that I actually implicitly I use the format UQ4.4. So what will be the value? What will be the real number value that I that binary number represent? Please quickly. Wow, if you do slowly, then you will miss some point in the final exam. Okay, so first of all, one answer come from Twin, 6.8 something, none 12.8, and then 6.8 something. Okay, actually, I think that maybe something 6 is correct, right? Because if I use 4 bit for the fraction, the binary point is somewhere over here, and the first part over here, the AH over here will be 6. So that's 6. That's correct, right? And the last one is what? Is 13. 13 divided by what? 13 divided by 16. Is that right? Am I right? Because now n equal to 4, so you have to divide by 2 to the 4, and 2 to the 4 is 16. So let me see. Let me do it right now. So come back to the scientific calculator, and then 13 divided by 16 equal to 0.8125. Wow, wonderful. So let me look at over here. Twin answer is correct. None is also correct. William, maybe you, please check again your calculation. Okay, so you understand. Everybody understand. Okay, that's one way to calculate. Okay, one way to calculate the value of a fixed point, the fixed point value of a binary number. Okay?
4, right?
Now there is another way. I teach you another way. Another way is you just look at forget about the decimal point over here, the binary point over here, right? Just look at the binary pattern over here, okay? The binary number over here, right? So that number, what is the integer value that binary number represent? Do you know? That's 109, right? We know that, right? So assume that the binary representation for that sequence is we call it IA, okay? So the fixed point value will be that integer value of this A bit, right? And then divided by 2 to the n. The n is the number bit of the fraction. So that's another way, right? So let use that way to calculate to see if you get the same number over here, okay? So let's see. Let's forget the point now, right? So the binary number represent 109, unsigned. Is that right? 109, okay? And then divided by 2 to the 3, because in this example, n equal to 3. So divided by 8. So 109 divided by 8 equal 13.625. Is that right? Yeah, please. All of you you are on the computer, please do that for me. Practice now. Even now, we already practiced for the final exam. Go ahead and do that to see if it's correct. So from now on, if I present you a binary number of 8 bits something, and I tell you implicitly, okay, I'm using the UQ5.3, and then I ask you, do you know what floating point, what real number that I want to represent, right? And you will tell me right away, okay, the binary, the integer value for that binary number is 109, and because you use 3 bits for fraction, so I should divide that one by 2 to the 3, meaning divided by 8, and the value is 13.625. Wonderful, yeah. So that's how you convert, how you find the true value, the fixed point value of a binary number, okay? A binary representation. Okay, so that's good. So you know Uqm.n, right? That's unsigned. How about okay. Actually, for this slide, is now I ask you in the reverse direction. Okay, so if I want to use a binary number to represent this real number in the format, in the fixed point format, 4.12, then can you do that? Can you somehow represent this real number using 32 bits, binary bits? Can you do that? Oh, actually 16. I'm sorry, 16 over here. So 4 bit for the 4 bit for they call for 4 bit for the integer part, and then 12 bit for the fraction part, right? So can you do that? Can you change to the binary representation, fixed point representation for this real value? Can you do that? Okay, follow this formula, right? Okay, follow this formula. So the true value that you want to represent is f over here, and you know that is 3.141593. Basically, this is a pi value, right? So you know that, you know f, right? So do you know n? Yes, you know, right? And I just asked you to represent in the format unsigned fixed point 4.12. So n equal to 12, right? So 2 raised to the power of 12, right? 2 raised to the power of 12 is about, let me see, is 4,096, I believe, right? I don't think I make a mistake there. 4,096, right? And then you just try to find the integer value over here, right? So the integer IA value here equal to f multiplied with the 2 to the 12. Is that right? Do you agree with me? Right. So here, first of all, I like to find out the integer value of the binary number first. So that so if I multiply 3.141593 with this one, I will get something like 12,867 something, right? But because this is an integer value, so I like to round them. So maybe round them to 12,868 like this, right? So now you just express this integer value in binary, and that's all. Probably, yeah. Please bring up the calculator. Bring up the calculator and change the integer value 12,868 to binary for me, to unsigned. Okay, unsigned binary. So what is that? I'm doing with you now. So let me enter that one. Okay, so decimal here. Let me 12868 and change to the binary. So I will get 0011. I will get 0011. 0010. 0100. 0100. Is that okay? Can you do that? Wonderful, right? Easy, huh? Can you do that? So if in the exam, if I ask you, okay, I like to express the real number 5.55 whatever into using the binary representation, fixed point representation, 16-bit with 5-bit for the integer part and 11-bit for the fraction part. Can you do that? Right? So you can see that we will get this one, right? Right? Okay. So now, what is the error? Of course, for fixed point representation over here, you cannot represent every number every real number, right? 0 to you can't, because the infinite number of representation. So basically, you have a gap in between. Okay, so there is an error in there, but the error is small. For example, this is the value expressed by this binary sequence over here. Okay, and this is the true value that you want to represent. It's a 3 point something like that. And if you calculate this one, then you will see that the error is just about 8 parts of a millionth, right? So it's pretty small, right? And this is a 16-bit. If you use 32 bits, right, and you increase the number of fraction over here, the error will be much smaller. Okay, understand? Okay, so that is unsigned number. How about signed number? How about signed fixed point representation? So I will do that. So for example, you have, let's say in this case, you have 8 bits over here, right? And you, and I tell you, okay, I will use this 8 bits to represent a signed fixed point number. So I will ask you, so what will be that number? Please let me know. So the way you look at it is, because I tell you, I like to use the n equal to, let me see. In this case, n equal to 3, of course, right? N equal to 4, right? And then we will use 1 bit for sign. The first bit is for sign, okay? If it is 1, it is negative. If it's 0, it's positive, okay? Okay, and the value, what real number it represents is very easy. You just treat this one. Forget the decimal point, the binary point over here. Just look at the integer value that these 8 bits represent. Okay, in 2's complement. Okay, so what is the value of these 8 bit in 2's complement? Can you tell me? Can you tell me that number? Let me see. I have a website on internet to convert between a number to the 2's complement. So let me see. Let me find that one over here.
If it's unsigned, then it'd probably be 18. But
yeah, this is okay. Oh, actually, I found that website. Okay. I found that website. So let me type in if the real number. Oh, actually, you know what? In this case, actually, very easy for us to actually manually calculate it. If I tell you this is a 2 complement numbers, right? So you can do something like that, right? This is a 1, right? Mm-hmm. This is 2, 4, 8, 16, right? 16, and then 32. 64, and then the last one, remember, that's a minus 128, okay? Minus 128, remember that. Okay, so calculate again. So 1 plus 2 is 3, and 3 plus 3 plus 16 will be 19, right? And this is a minus 128 plus 19. It is minus 109, right? And then you divide it by 2 to the n over here, n bits over here. I told you we will use 3 bits for the fraction. So the number that we want to represent is actually minus 13,625. Understand? Easy? Right. So that's a very easy. So let me go to the next slide over here. Okay. So now, as usual, I will ask you to convert from the real number to the fixed point binary representation, right, in the reverse direction, to see if you can do that. So the same thing. So if I ask you to do to represent the real number minus 3.14 something in this format, in the psi format, right? 3.12 over here. So what will be the number, right? So the same thing. First of all, find out the integer value that the binary number represent, right? So by multiplying f with 2 to the n, okay? So in this case, you multiply f by this one, and you will get minus something over here. And please route it, right? Because we can. This is not an integer number, so please route it to this negative number over here, right? So the only last step is to change this negative integer number to binary, and that's all, 16-bit. So there are a lot of ways to do. Maybe you can bring up the website that I'm using to change from a negative number to two's complement, right? Or maybe you can do the way that you learned before. Maybe you do try to find the represent for the positive first, right? And this for the positive, and then we take the 2 complement, right? And for the positive 1, 2a, 6a, we just found it, right? We just did it in here, right? So the positive number is where is that? Yeah, it's this one, right? Okay. So now you want to find the negative of that one. So just invert all the bit of this one, right? Basically find the 1's complement and then add 1. Is it right? So invert all of this one. You will have 1 1 0 0 1 1 0 1 1 0 1 1 1 0 1 1 and then plus 1, right? So you can see in this case, I invert everything. I will have this one 0 0 1 1. Here, right? What? Yeah. Do the way that I just tell you, and then finally, after adding 1, you will have something like that, right? And that is the signed fixed point representation of this real number over here. Understand? Easy, right? And the same way, the error you can see is the error is very, very small. Okay. So let's do 2 more slides, and we will stop. Okay. So I have an example for you. I have a very short example. Let me see. Let me bring up. Okay. So now, assume that you have to answer to give me a response. Okay. Otherwise, I will not proceed. Okay. A very simple example anyway. Okay. So let me set up the question. I will use 4 bits instead of 8 bits or 16-bit. Okay. Very simple. I will use 4 bits binary number. Okay. And that number is to represent. I mean, I use that one 4-bit binary number to represent a real number using the fixed point representation, unsigned fixed point. Okay. And I will use the first 3 bits for the integer part and the last bit for the fraction part. Okay. Understand? So basically n equal to 1 and m equals 3. Okay. So now the binary number is 0011. So what is the real number that I am representing in the format UQ3.1? Go ahead. Very simple. The binary number is 0011. Okay, 0011, and I use just 1 bit for fraction. Basically, n equal to 1. So what is that real number that I want to represent? Please let me know. Quickly. Too slow.
Yeah, I'm just trying to figure out.
Yes.
0011.
The binary number that I want to have is that. Okay, and I tell you n equal to 1. So basically, I use 1 bit for the fraction, and then 3 bit for the integer part. So what real number is that I want? I'm using the format Q3.1. Mohammed answer is 1.5. Anybody? Twin is 0.75. Anybody else?
This is for one of the F's.
Ismail, none is 1.5. Okay, so for 1.5 is correct. So for you, get one with the answer 1.5, you got 100 points. Okay,
that makes sense because you're doing 3 over 2.
Very easy, right? Because 0 1011 is 3, basically, right? Is that right? And then you divide it by 2 to the n, 2 to the n, right? And n in this case is 1. So basically, you just divide it by 2. So 3 divided by, 3 divided by 2. So you get 1.5. Easy, right?
Mm-hmm.
How easy is it? Extremely easy, right? Okay, so I will ask you a little more. One more. Just try to do one more example with me, okay? So the same thing, I will use the a binary 4-bit binary number, and I would tell you that the format I use is unsigned again. Unsigned UQm 3.1. I mean the same thing. I will use that one, and I will give you 4 bits now binary. Okay, so let's see. How about 1101? Oh, I mean, no. 1011. Okay, what is that number? Quickly, what is that number? What is the real number that I am representing? Quickly, everybody. William, remember, I use only one.
Yeah,
you're right.
I flipped the mind a bit for 2.2. I thought UQ 2.2 for a second there. Sorry about that.
The Matthew answer is 5.5. Anybody, quickly, twin, 5.5. That's wonderful. Yeah, that's correct. Yeah. So 1011 is basically 11 in decimal. Is that right? 11 in decimal.
Right.
So we divided by what? N equal to 1, so divided by 2, right?
So that's
11 divided by 2 is 5.5. Simple. So that's the real number that I actually that's the value of 1101 in the format of UQ 3.1, right? Okay. So now I like to add these two numbers together. Okay. I like to add. Remember, I tell you, I'm using the UQ 3.1 format. Okay. So I like to add the two number 0011. Add with 1011. Okay. So what do you think?
What do I get? 0011.
So what do I get in the fixed point representation? Okay, so for example, just ignore about fixed point or anything, right? So let's assume that I just use a binary binary adder to add them, right? Like the hardware doesn't know anything. The hardware doesn't know it is an integer or it's fixed point. You are the programmers, so you know what it is, right? So we just throw at the adder for it to calculate. So can you add on paper for me 0011 plus 1011? Okay, so what do you get? So if you add these two binary numbers, probably you get something like 1110. Is that right? Wonderful. Okay. Very good. Yeah. If you ignore everything else, you just add in terms of binary, you get a 1110, right? Okay. So now I will ask you, what is 1110 represents? I mean, what does the 1110 represent? So what is that? Right? So again, too, 1110 is 14. Is that right? Right? 1110 is actually 14 in decimal. Is that right? And then, because I tell you the format I use is UQ 3.1, right? So you divide it by 2 then, right? So 14 divided by 2 is 7. So that is 7. And it turned out that 7 is exactly the same as 1.5 plus 5.5 before, right? So it's amazing that if you deal with fixed point and you do the addition of fixed point, right? You just do exactly the same as with integer, okay? You just go ahead and add these two numbers as if they were integers, okay? And then only at the end, you divide it by 2 to the n, and that's all, right? So you can see you can see over here, right? So if you add the two fixed point number, please go ahead and add the binary representation exactly, right? And then at the end, if you really want to interpret what is it, the sum, right? So you just divide it by 2n, that's all. So adding or subtracting two fixed point numbers is performed in the same way, exactly the same way, as if the 2-bit string were represent two integers. Wonderful, wonderful. That's why it's so cheap to use a fixed point representation to do calculation, to do real number calculation, right? Because the hardware just the hardware think that, oh, you are dealing with the integer. In fact, in C, when you declare these, you declare them to be integer, actually, 8-bit integer. So you can see from now on over here. So if you say that, oh, R0 is, you store a fixed point number, and then FA, and then R1 store a fixed point number FB, right? So how to calculate the sum? All how to do the addition or subtraction. So you go ahead and do as normal for me with the integer, right? So you use the same instruction to add the fixed point, and you use the same subtract SUB over here to subtract the fixed point number for me, and everything will work out okay. Understand? Let me answer. William said, wouldn't this only work if n1 equal to n2?
As in, like, the UQs.
Oh, of course. That's a good number. Of course. They have to use the same representation, of course, right?
Yeah, but I mean,
you can say, oh, sometimes I will use 16 for fraction, and some other time I will use 15. Oh, it doesn't work for the whole program. Of course, you have to implicitly assume that the number of bits for fractions is fixed. Okay, 16 in this case, for example. Okay. Okay. So with that, I'd like to stop over here. And then for next Monday, I will continue with the fixed point for multiplication and with division. Okay, so at least for add and subtract, addition and subtraction, we'll go ahead and to do as normal. Use the same instruction for integer. Okay, and do it. So it will work out okay. Okay, but what? How about for multiplication and division? Maybe we need to modify a little bit. Okay, it will not be that nice anymore. We will modify something. Okay, so next Monday we will talk about that. Okay, so with that, please take a break, a 5 minutes break. Okay, so during that time, I will release the grade midterm 2 part 2 grade for you, and also release a midterm for you to see what you did as well. Okay. So we will come back in 5 minutes, and I will talk about the solution. Okay?